So go ahead and get the live stream rocking. All right, looks like it's going there. Thanks for being here on time. Appreciate it. So we've got a bunch of junk. I sent out a bunch of stuff earlier in a chat. Actually, I better hit pause on this broadcast. Hold on a second. Turns out when I hit live stream, it starts playing at about 20 seconds afterwards. So I have to remember to hit pause every time. Whatever. We're done. And so what do we want to talk about today? Circular motion. I sent out an email that was explaining some ranting and raving I did in the earlier class. I'll spare you. I ranted and raved at you last time. So we'll just trade off which class has to bear the brunt of my irritation with online learning. That said, let's talk about circular motion and kind of review a few things, all right? So let me go to speaker view here, get me up there. And let's kind of go back to some. So all day today, we're just going to be doing circular motion force problems. And so let's review a few things about that we learned last time, maybe just to kind of get you warmed up. All right. We talked about there's some acceleration, right? And we talked about that's got AC in the negative r hat. Plus a tangential, and that's either in the plus or minus theta hat. Now, for right now, we don't really need to worry about this r hat and theta hat and what they mean that much, but it's kind of good to just kind of get a feeling for them. You'll use that more in a dynamics class, or maybe even next semester in Physics 163. R hat means radially outwards, so negative r hat means radially inwards. So that's just kind of our standard stuff there. All right. And so if you recall, AC was V squared over R. And now I just want you to get used to this term as well. This is also R omega squared. So omega was like your RPMs or your rotation rate. And it turns out omega was given by 2 pi over the period. All right, so T was the period. And this stuff is on page 111 in your workbook, if I recall correctly. So if you want to kind of have that handy, you could open your workbook to page 111 right now. I'll get a sip of water and let you do that. All right. Now, one of the things that's kind of sneaky about this, velocity, and sometimes this is called tangential velocity. I should be careful. This right now it's written as a speed, but okay. Tangential speed is not your omega, it's r omega. All right. So we see here that we have to be careful, and a quick unit check is worthwhile here. So radius has units of meters. Omega is in units of radians per second. Now, and when you multiply anything times radians is just a placeholder. It gets absorbed. We get meters per second. Whereas up here, we get meters times radians per second quantity squared. We get meters per second squared, as we should. So that's something you could just kind of, if you are trying to remember, wait, is it r omega? Is it r omega squared? You could check the units and that'll tell you what the equation is, or look at the back of the book and it's written on my equation sheet on the back of the workbook. All right. So these were some things. Let's see. What else did I want to say about this? Generally speaking, we talked about some coordinate systems. So if you have something moving in a circle here, right, and you're at some arbitrary spot, we mentioned r hat is going to be, whoops, that's not quite outwards. That points towards the center, so that points away from the center. R hat is away from the center. You're going to see me use this today, centripetal hat. So that just means a direction pointing towards the center. It's a bit non-standard. And then what I was mentioning earlier about the theta hat, whoops. Theta hat was a term we're using. The standard definition of theta hat is counterclockwise around this circle. right? Now for us, sometimes in a physics class, we'll get sneaky and we'll call this way theta hat if everything is rotating that way. So go ahead. A question about that or? All right. Okay. So these were, now I want to think about one more thing before we get into the FBDs that's kind of a source of confusion. Now let's talk about this direction right here. Right? Coming out of the page. A good name for that is the Z direction. So now, if you recall, it's kind of hard to squeeze it in here, so I'm going to draw it right here. That's the K hat direction or the Z direction, okay? So if you recall from the vector chapter, this symbol means into the page. And this symbol right here means out of the page. So right here, I like to remember this by thinking of the dot as being like an arrow flying out of the screen to hit you, and the X being like the feathers of the arrow flying away from you. So this is supposed to be out of the page, meaning away. Whoops, I switched them, didn't I? Sorry about that. That was a total mistake. X is into the page, flying away from you into the page. Sorry, I misspoke there. All right. So I drew it correctly over here, but then I wrote the words into and out of incorrectly a minute ago. Now this is correct. Dot means out of the page, pointing out at you. X means feathers flying away. All right. So let's look at this one more way. What if I tilt this on its side, and so we have a circle going around like this? So this would be a top view, and this would be a side view of the same circular motion. All right. Notice towards the center here would point this way. Into the page would be tangential or theta hat. What direction is this now? So again, I took this and I just laid it flat. I took this circle and laid it flat.
Is it radius?
Nope. Radius would be opposite C hat. So R hat would be that way.
So it's K hat.
K hat. And sometimes you'll see me use K hat, or sometimes you'll see me label this with a Z for the Z direction. Now, in circular motion problems, here's the deal. Usually one viewpoint, say the top view, is great for seeing the circle. But a side view is sometimes better for drawing an FBD. And so one of the things we had to do in this chapter that we didn't have to do sometimes before is you're going to have to draw multiple pictures to get a good feeling for what's going on in the problem. All right. And sometimes you're going to see things labeled with C hat, sometimes labeled with Z, sometimes theta hat, sometimes R hat. All of these different things get used. But most of our pictures are either going to be C hat and theta hat, or basically C hat and tangential, or C hat and Z, or C hat and K hat. Okay. And so I'm going to tend to avoid the R hat direction because I don't like getting the minus signs wrong. All right. And so just as an example of that, imagine we have this ball here. Whoops. It's swinging around in a circle. I don't know if you could tell that. If I could, let's try and make it go around this. There you go. So notice in this case, theta hat would be this way, tangent to the circle. Z would be this way, and centripetal hat and radius hat kind of depends on which way you're pointing. So if this circle is going this way, R hat would point out of the circle, and C hat would be pointing towards the center of the circle. So we see that even in this simple example, theta hat is at any point tangent to the circle, right? So obviously theta hat in the front would be this way, theta hat in the back would be this way, and here it's this way, and here. So theta hat and r hat are constantly changing. So what we oftentimes do is we'll draw a picture at one random instant in time and try and figure stuff out rather than worrying about how this thing evolves in time. We'll take a snapshot. Without further ado, let's take a look at a physics problem here. Let's see, I lost it. Oh, I forgot to, let me see here. Whoops. Oh, man. Sorry about that. There we go. And so let's just go up here to about page 120. I don't know. Let's see. Oh, that's too far. Let's try 117. All right, we'll start with this one. So this is page 115 in your book, 117 in the file that I have. There's problems before this, and I'm hoping that these ones are easier for you to attack at home on your own. I think they're great problems, but these first couple, 652, 53, 54, basically everything on page 114, there is no shame at all in having the solutions open while you do those. And then hopefully after doing those, you can put the solutions away and attack things by yourself. All right, so swing the bucket of water. This is a classic demo. Now, it's a little bit tricky here. So let me do this. Hold on a sec. All right, so give me a second. Okay. Now in a second here, I'm going to have to put down the headphones. This is a very small room. Okay, nothing up my sleeve. It's not like I glued this cup to here. And this is a small room with a lot of stuff I can break. So instead of pouring water in this cup right now, I'll just pour in some ping pong balls, all right? And so just to be clear, those are not glued in there at all. Now, I'm just going to take this. I'm going to back up and I'm going to pull my headphones off. So sorry if I have to shout. I don't know if you can hear me or not. All right. Small room. There they go. So this works. This totally works. Oh man. I could do it with this cup of water here, but I don't feel like, what if I make a mistake and totally ruin everything on here? And oh, maybe my Zoom would crash and I could quit. Okay, let's do it. No. Jeez. All right, so let's do this problem and analyze it. It's a fun one to do. All right. So to simplify the problem, we're going to assume it swings at constant speed. Is that a good assumption? That's a big assumption to make. Where'd that ball on a string go? Here it is. I just want to show you that this is actually somewhat reasonable under certain circumstances. Now think about this. As the ball goes up, gravity is pulling down on it and slowing it down. All right. And I could even show you that with this. We know that that's happening here with this one. You can see it slow down as it goes up, right? Oh, I'm giving it a jerk once in a while. But so clearly we expect things to slow down. However, if you put this thing on here and go crazy, think about the time it takes to travel from the bottom to the top. It takes such a small amount of time. Yeah, it's going to slow down, but the amount it slows down is very, very small compared to the speed at which it's moving. Similarly, it's going to speed up on the way back down, but the amount of time it takes to go up and down is somewhat negligible. So again, if we spin this thing fast enough, it definitely slows down on the way up and it speeds up on the way down, but that's somewhat negligible until we go really slow like this. And then at some point, just like this one, if I go too slow, you notice the ball turns into a projectile at the top. So instead of having the string stay taut, you see the string kind of fall apart like this. You see the string kind of go, all right? All right. So let's try to analyze this. That's just getting you a feel for this problem. All right. So we're going to assume it swings at constant speed for now, just to simplify the discussion. All right. Draw an FBD and write down a force equation for the water in the bucket at the top. Okay, so here's the bucket. And then here's the water in it. Okay. So what are the forces on the water?
Gravity.
Gravity. All right. mg, got it. What else is exerting a force on the water?
Would tension be one of them?
So my arm is holding the bucket, and so there's tension in my arm on the bucket. Is that on the water?
No.
No. What's actually touching the water?
The bucket.
The bucket. So it's a
Normal force.
normal force. Which way?
Down.
Down. I guess I kind of gave it away there by starting to draw, but yeah. The idea here is, think about it. When you swing very quickly, let me go back to this example. What happened to all my glasses? All right, whatever. They're flying all over the room. Let's simplify this discussion a little bit. With this case right here, the ping pong ball is the water. The cup, all right, is the bucket. And so you could see as this thing goes up, you kind of think about it. We know that the tray has to push on the cup, and in turn, the cup is pushing upwards on the ball right here. And when we go to some angle, the same thing is true, right? There's a normal force going this way onto the bucket. That bucket transmits that information. Now, where does this all come from? Ultimately, it comes from me holding the string. So there's tension involved in the problem, but the actual force on the ball itself is a normal force from the cup. That normal force wouldn't be there if I wasn't pulling on this string, though. All right, so it is related to that tension. All right, going back. So, all right, so actually we can go to the whiteboard now. Whoops, it's way back there. Okay, so let's draw this again. You guys already did it correctly, but let's write it down. Okay, there's a normal force, there's mg. They're both pointed down, and here's the water. We'll just draw the water as a dot. Right now, remember, it's in circular motion. So what direction is the acceleration? It's at constant speed. Is there acceleration?
No.
Yes, there is. Just because you're at constant speed doesn't mean velocity is constant. Case and point. Right before, velocity up. Right after, velocity down. The change in velocity is which direction?
Down.
Down. There's no change in speed, but there is a change in direction. So there is an acceleration towards the center. Now, if there's no change in speed, is there any acceleration tangent to the curve?
No.
No. And so that is, and maybe that's the component you meant. A tan is equal to 0 in this problem. We are told, so if V equals constant, tangential acceleration is 0, but there's still a centripetal component. All right. Why is this a bad idea right here? Why is this bad? Why should I not draw this on this FBD?
It's going down as well as that way, so it's not going straight left.
Nope.
Because it's not a force.
It's not a force. So velocity is not a force, so we shouldn't draw it on an FBD. That was drawn in the correct direction for this instant in time. But now you're right. A second later, it would be going this way, and then later, yeah. But so just trying to remind you, the FBD, we're only drawing the forces. Okay. So what's the force equation here? If it helps, let's say this is theta hat, and this direction is centripetal hat, right? Give me a force and whether it should be plus or minus.
Is it N plus mg equals MAC?
Okay, and let's check. So this is a good time to use this. Look, all three vectors point the same way, should get the same sign. We do. Looking good. Wait. What's the force towards the outside of the circle? What's the force pushing the ball to the outside of the circle? Or the water or whatever.
There's no force, right?
There isn't one. There isn't one. All right. So these FBDs feel uncomfortable because we're used to having forces. So what? This is the deal. At the top of the circle, all the forces are down, the acceleration down. That's fine, right? If you have unbalanced forces, you can have an acceleration. Nothing here is weird. All right. Now let me ask you something. As this cup or this water or whatever is spinning, what happens to the normal force when the ball falls out? What's the normal force from the cup on the ball right now?
Nothing.
Nothing. So now think. This is the special condition that we are going to use all the time for something losing contact. If you lose contact with the surface, what is your normal force? 0. So if losing contact, normal force goes to 0. This should tell us something about the speed. That's my claim. Where does the speed show up in this problem? I don't see it right now. Where is the speed hidden?
In the AC?
AC. V squared over R. So a lot of problems are going to ask you about speed and radius in this chapter or something like that. And then you have to think, oh, well, that's hidden in AC. It's there. So you do an FBD, you write some force equations, plug in this crap, solve for something. Same as any other problem, all right? So now let's set n equal to 0 and do some simplifications here. If n goes to 0, what drops out?
Mass?
Mass drops out. And then we get v squared. Hopefully you see that v equals the square root of rg. Take a second to kind of think that through. My apologies. Let me lower this down a little bit. Right? Because this has got v squared over r. You cross multiply, so you get rg equals v squared, and you square root. Okay. Is this a minimum or a maximum speed?
Minimum?
Minimum. If you go too slow, the water falls out of the bucket. What happens if you go really fast? If you go really fast, what happens to the normal force?
It should increase.
Yeah, so this is what happens. The normal force will get huge if you go really fast, but that doesn't mean the water is going to pour out. The water pours out if you go too slowly, and this is the critical speed. So I'm going to label this as a minimum. Now, very common in these problems is we then say, well, what's the period associated with this? How do you get period? Does anybody remember?
Mm,
Let's use distance equals rate times time. We could do that because the speed is constant. What's the distance around a circle, any circle?
Pi r 2 squared. pi.
Pi r squared is the area, 2 pi r is the distance. What's the name for time around one cycle?
A period.
Period.
Period. What are the units of this?
Radians
per second.
Radius per second, which is meters per second, which is distance over time equals speed. If you're not accelerating. Wait, I thought we were accelerating. Yes, but a tangent is 0. Oh, something just came out. Can you still hear me?
Yeah.
Okay, you could. Okay, I heard something weird. I don't know what happened. Whatever, some cable. All right, sorry about that. So just be careful with that. All right. That weird sound just came again. I'm assuming you could still hear me, hopefully. Sorry about that. I don't know what's going on there. I think when I'm lifting this up and down, I must have hit something in the back somewhere of my computer. I'm not going to worry
You
about
sound
it.
fine. So
All right, cool. Thanks. Appreciate it. All right. So let's say we plug in, this is a minimum. I hope you agree we could somehow figure out the period here. Is this period going to be a minimum or a maximum? If I'm at the minimum speed, my period or time is a
maximum.
maximum. So watch out for this. In these problems, I don't know why, but personally, I have to think carefully about min and max because they're right. If I say a maximum period, that means a minimum speed. But if I say a minimum period, that means a maximum speed. And they both come up occasionally. So as you do more and more of these problems, just be careful here. Min or max, period or velocity, they both show up a lot of time. Okay. All right. So in this case, let's just show you that this works one last time. That's water in there. I better not screw this up. Okay, this will give you something to laugh about. And I better not screw up here. Turns out the easy part is getting it going. The hard part's stopping it without spilling. All right. Yeah. There we go. Physics works. Oh man, I'm looking at all these books thinking, God, I've got all my notes on the floor. I'm like, oh shit, I better not spill. All right. So it works. Now the trick is just make sure you go really fast. And here's, if you want to know how to stop, I love doing this to students. I used to bring in all the glassware and then tell them, all right, try it. It's easy, but it's easy to get it going. The trick is stopping without smashing things. And so the trick is when you're trying to get this to stop, as it's coming down, don't stop at the bottom, stop right up here. So let it go past, and then you can stop it like that pretty easily. So basically at the bottom, let it pendulum to stop rather than trying to stop it right away. It's the trick. All right. Always fun breaking glass with students. Sorry we don't get that right now. Questions about that? It's kind of a fun one. Okay. All right. So let's see. I think we've pretty much nailed it. All right. We've covered everything in there. All right. Now, something I might mention here, this is worth saying. I don't remember if I've said this today or not, but you got to watch out for ball on a string versus ball on a rod swinging. Okay. So the idea is here. If you have a ball on a string and it's swinging around, strings have to exert a tension, right? They can't hold the ball up at the top, right? The string can't exert an upwards force. Whereas if you have something like this, right? This is a rod at the top. It could actually be supported. And so the minimum speed for this one at the top is actually what? If I could get it to work there. What's it look like? The minimum speed for this weirdo thing is
0.
0 at the top. And I don't know what I'm doing, but this thing's totally falling apart. I better be careful here. We'll fix it later. It's taken some abuse today. All right. Whoops, cables everywhere. All right. So just be aware of that. And so when you look at these problems, a lot of times they look the same. But so like if you look at this picture over here, it's really hard to tell the difference between a string and a stiff rod that's holding up the two spheres or whatever. So just be careful on that one. All right. And then again, we said at high velocities, we know that the amount of time that gravity is accelerating it on the way up or way down is negligible. And so there are small changes in the speed, but not significant. And then let me get, is it this one? No, that's this. Hold on. Got so many zoom windows here. Is it this one? There we go. All right. Let's take a look at this gravitron. Okay, so now this is the next problem in the workbook here. 657. All right, and so let's take a look at this before we show it. We've got a barrel of fun. It gradually spins faster and faster. Ding, ding, ding. An alarm bell just went off in my brain. When I see gradually spins faster and faster, that tells me something about this problem. That tells me something is approximately equal to 0. What? Take a guess. It's okay to be wrong.
Acceleration?
Which acceleration?
The centripetal?
No.
No, that's towards the center. The
tan. A-tan.
Other one, yeah.
Yeah. So the idea is atangential talks about changes in speed. So whenever you see something where it's gradually spinning faster, that's basically synonymous for saying atangential is approximately 0. Okay? So or said another way is the tangential forces in the problem are negligible. Okay, so watch out for that one. Give me a coordinate system on this one. What direction is towards the center of the circle? Is it up, down, right, left? For the instance shown.
Left.
Yeah, so this is AC, right? So there's AC. What direction is this? Is it theta hat or Z?
Z.
Z. And this is what's kind of weird. It looks like it's tangent to the circle. It is tangent to the circle, or maybe you want to call it K hat. All right. So we see that there's a logical direction to choose here. This looks like towards the center. So I'm going to call that C hat and Z hat or K hat or whatever you want to call it. Okay. So notice theta hat would actually be in the direction it's rotating, and it's kind of hard to draw that. So theta hat would either be a dot or an X, depending on which way it's rotating. Okay, so that would be theta hat. All right, enough on that. Okay, we know it's accelerating. Give me a force here. One of the forces on it. It's okay to be wrong.
Force.
Which way does that point?
Towards the center.
Yeah, so in this case, now the normal force is pointing this way. Okay, give me another force.
mg of the person going down.
mg straight down. Got it. What's holding the person up when the floor drops?
Normal force.
Nope. What's usually at right
Friction.
angles to the normal force? Friction. Friction holds it up. Now think about that. As long as normal force and friction are at right angles, we usually say, okay, that looks pretty normal. So this is very weird. Normally we have a block on this side where the surface is right here. And then we think normal force is up and frictional force is that way. Well, now we have a situation where the surface is over here, the normal force is this way, and friction is this way. That doesn't seem that weird. It's basically rotating the picture 90 degrees. Hold on, let me get that out of the way. Any questions on that? All right. Let me get rid of these two dots too. All right. So in this case, let's write the force equations. And just to be clear, let's write them like we said. Let's say we're doing this coordinate system where this is z and this is towards the center. You could do z hat or k hat, whatever you want. All right. Give me a force equation. Anybody. It's okay to be wrong. Try it.
N equals MAC.
That's correct. Let's check. Same sign, pointing same direction, looks good. Next, what's the other one?
Frictional forces minus mg equals m.
How much
This-
is it accelerating in the z direction?
So 0. So then this is going to be frictional forces equals mg then. Correct?
Yep. Cool. Now we've got to be careful. Read this sentence right here. Determine the largest possible blah, blah, blah that allows the person. Okay. So it says largest possible period. Is this thing spinning quickly or slowly?
Slowly.
Slowly. It's a large period. That means it's a slow motion. Okay. So should I use F equals mu kinetic times the normal force, or F equals mu static times the normal force, or should I not use either of those? What do you think?
Mu static.
Yeah, it says largest possible. That means if we weren't at that special extreme value, it would slip. So this means it's on the verge of slipping. So it's okay to use mu static times the normal force for this one. Okay. All right. So when I do that, that becomes mu static times the normal force. Notice what happens here when you take a ratio. What drops out on each side?
Mass and the normal force.
And then we're going to, let's see, what do we get here? I think we get mu static equals G over AC. Now you could go ahead and solve this for velocity or period or whatever, and I think you could solve the rest. But hopefully you agree that from here, if I need the period, what do I have to do? How do I get the period involved? Just give me the steps. It's okay to not get it in one step. What would you do next?
Change the AC to v squared over r.
Okay, we could stick in v squared over r for that. Then what?
Substitute omega for 2 pi over a period.
Okay, but we don't have omega. Maybe what you're saying is you could do this. You could say, so here's another style. You could say that's r omega squared,
Yeah.
and then you could plug, that's fine. You said, what is omega?
Yeah. Substitute that for 2 pi over period.
That would work. And then how would you do it if you had used velocity? What's the equation that relates velocity and period?
Is
Is it
it
like
two?
Over period.
Yeah, that 2 pi r over period. So we see a couple different ways to approach this. And this is kind of why it's more fun, but also more challenging here is there's many different correct ways to get an answer here. And so they're both equally valid. So when you're communicating with others, it gets trickier because you kind of need to know more than one way. But I hope you agree at some point you could shove all that crap in and solve for t, right? And it's just a matter of doing it. And you could do that at home. All right. Let me ask you this. Does the mass matter?
No.
Mm-mm. We see that the mass doesn't matter. So this should work the same whether we use a full-grown woman or a little child or Andre the Giant, if he was reanimated corpse, came out of a zombie grave and started to play in this area. Anything you want. Now, wait a minute. That doesn't seem reasonable. It turns out not everybody wears the same clothes, and the different clothes might give you different coefficients of friction. So your clothing matters more than your weight in this type of problem. So yeah, just so obviously there are some different factors there. All right, that said, let's go to this last one. As the rotation rate doubles, what do you think is going to happen? So let's say we go twice as fast. Okay, what's going to happen to AC if you go twice as fast? Increase, decrease, or stay the same?
Increase.
By what factor?
2.
4, because it's v squared. Right? If you double the speed, you quadruple AC. Got it? So watch out for that. I was trying to trick you. I got you. Okay, how about the normal force? Is that going to stay the same or not?
I think it'll increase as well, right?
By what factor?
That one will be 2.
4. If AC, remember, the normal force equals MAC. That was the force equation in the center direction. And so if this goes up, if the speed doubles, this goes up by 4. That means this has to go up by 4. Are you okay with that?
Yeah.
Yep. All right. So if the normal force goes up by 4, what should happen to the frictional force?
Four.
Nothing. It's still balancing the weight. What happens is if you double the rotation rate, it's no longer the largest possible period. We're no longer on the verge of slipping. Friction is now less than mu static times the normal force. Don't you love physics? Oh, that's sneaky. I was trying to set you up for that and I got you. Watch out for this. Does that make sense there, Jess?
Wait,
Yes.
Can you explain that one more time?
Okay, so remember, as you double the rotation rate, you're no longer on the verge of slipping. If you're no longer on the verge of slipping, the less than now applies. And I could tell you another way. What if I did the force equations? F equals mg, right? That's it. This is the same whether you're going fast or slow. So usually you want to go faster. That way you're not right on the verge of slipping for somebody to fall down. And then they say, this ride stinks. I didn't even get to levitate off the ground. All right. Said another way, think about it. What if the frictional force suddenly became 4 times larger? 1, 2, 3, 4. That would mean it would start sliding upwards because of friction. That makes no sense. Agreed?
Agreed.
And so if you kind of have to think about the FBD carefully, and you have to think about these frictional conditions carefully. So basically what I'm saying is this. Just because part A used a special condition for friction doesn't mean other parts of the problem get to use the same condition. All right. So that's sneaky. Now, when you look at this, Okay. Let's just go normal speed here. So what I'm going to do here, you can see I'm getting this cylinder up to speed. So I'm just spinning it really fast. And what I do is I make sure I'm going too fast. And I put the eraser, that's an eraser on there. So just to pause at a split second. So that's an eraser stuck to the inner wall of there. And so I used an eraser because it's got a high coefficient of friction, close to 1, hopefully. And so now what I'm doing is I'm touching the edge of the cylinder. It looks like I'm just putting my hand in space. I'm actually slowing it down by gently dragging my fingers. I'm causing a very small atangential in the negative direction. I'm slowing it down slightly with my hand, but I'm trying to do it very gradually so I don't just knock the eraser off. So now right about here, I think it falls down. So I'm going to go to slow-mo. So you can see the eraser is stuck there. And right about here, it starts to drop. And so it dropped to the ground there. And that is the instant in time when there was no longer sufficient friction to hold it up. And so from here, you could actually count the period using the clock on the screen. And okay, we got it. It's about a second. You could figure it out, blah, blah, blah. All right. So that's enough on that one. Questions on that? Is that making some sense? Very sneaky problems. There's not a lot of forces, a lot of right angles, but it's just like, oh, you have to think. That's why physicists like this. It's I don't know, whatever. Let's keep rocking here. All right. Let me escape out of this. Hold on. Get out of that. Whoops. What did I do? All right, there's that. Let me get back to this one. Here we go. So next page, which flies off first? Okay, I'll let you have a second to read it. Okay. Put a bunch of blocks on here, different sizes. And let's just assume each block is the same distance from the center, as you can see in the top view. We've got some coefficients of friction. What's your gut tell you? You got a heavy block and a light block. Which one do you think is going to fly off first? Usually it's not going to be one of the middle ones. Is it going to be the heaviest or the lightest? What's your gut tell you?
The heaviest.
Okay. What's your
wait, no, the lightest.
Okay, what's your reasoning?
Well, so okay. Because more mass means it's gonna have less tendency to move. You need more force, right? So
all right,
so if
I
you
got your
apply
idea.
little friction, then the small one's gonna go off first, and then
Okay. So let's do the FBD. So let's do an FBD of this one and see what it tells us. There's a normal force up. There's an mg down. What force causes this thing to go in a circle? What keeps this thing from flying off the table?
Friction?
Friction. Which way does it point for this mass right here at this point in time?
To the right.
Mm.
Or yes.
So,
Wait, no left.
Yeah, friction doesn't push it outwards, does it? Friction points to the left. What is the force that pushes it outwards?
AC?
AC is an acceleration. It's not a force. What is the force that pushes outwards on that block? I like what I'm hearing. Silence. What's the correct answer?
Nothing then.
There isn't a force that pushes it outwards. When you move in a circle, you need a force towards the center There is no force pushing you to the outside. And that's something we have to get used to. Later on in today's class, if I get to it, I'll explain how what you were mentioning about AC relates to a fictitious force that we perceive that isn't there. Okay? So in this case, that's the FBD. It's accelerating towards the center. And this makes sense. There's a force towards the center. There's an acceleration towards the center. Again, the velocity was going this way. Afterwards, the velocity is going that way. The change in velocity is this direction. There's acceleration towards the center of the circle because there's friction. If there was no friction, what would happen when you spin the turntable? If there was no friction, which way would this block move?
To the right.
It wouldn't move at all. It'd just sit there because the table would spin underneath it and there'd be no force touching the block, right? There'd be so it's super weird. If there was no friction, the blocks would just sit there like ice cubes on Teflon as you spin the pan beneath them. Weird, right? It's just super counterintuitive. All right. So there has to be friction, otherwise it wouldn't move in a circle. That's what that was supposed to be for. All right, let's do the Fbd force equations. I guess we did the Fbd. Let's do the force equations. So based on this picture, again, I'm looking at a side view. So I'm going to say Fbd side here, just so you know. If we're doing a side view, give me one force equation. Somebody new, take a chance. It's okay to be wrong. By speaking up, you improve your grades, even if you're wrong, it turns out. Somebody new, try it. It's okay to be wrong. I'll be nice to you even. Oh, there's somebody in the chat. Okay, let's check it out. N equals mg, right on. Perfect. Thank you. Nice job, Jesus. N equals mg. Smart move. Take the easy one. Actually, the other one's not too bad. What do we get from these two? Somebody else. You could throw it in the chat. That way you don't have to speak up. It's okay to be wrong. All right, anybody? Anybody?
Is it F equals MAC?
Yes, it is. F equals MAC. Oh, thank you, Mark. Thank you, Mark. So, all right. So Mark responded in the chat, but he sent a private message. I got you. So be careful, Mark. I think you had a typo there. So look, this is the force. And then, okay, got it. Yeah. So you did. Yeah, you got the right idea there. Good. Thanks. Okay. So in this case, if I take a ratio, what drops out?
The mass.
What do you think, Jacob? Which flies off first? Does the mass matter?
No.
No. Oh, so they both fly off at the same time?
Okay, so in here, this looks really strange. Let me explain what's going on. Right here, there's a hanging mass, and it goes over this really big pulley, and it comes down, and then it comes in here, and then it wraps around like 100 times around the bottom of this thing. So that's my trick, is I use a tiny mass, and we wrap it around the axle, and we pull on this thing, and it will very gradually spin this thing up. Okay, and so by doing that, that's how I get A tan equal to 0. And so when we do this one, give me a sec. So just to show you, I'm not lying to you. there's 4 little pieces of plastic, and that one's 34 grams. And basically, in each one of these little plastic tubs, I put some masses. I just had some big washers, and I tried to tape them all exactly in the middle. I did the best I could, taping them all exactly in the middle. And now I'm trying to place them precisely at the same radius. And it's very boring to watch this, so I'm playing it at double speed. And we're probably going to have to skip forward a bit. Oh, look. So notice that hanging mass is moving upwards right here. So that's the mass that's going to cause these to accelerate. Okay, and then hold on. Oh, wait. Oh, did you see that? Hopefully you saw that. They all fell off at the same rate. Let's go back. Sorry, let me go to normal. Actually, let's go to quarter speed, and we'll go right to the end. Okay, here we go. The stare of death. Okay, that's a little too slow. Oh, there it goes. Very slowly accelerating. And look at that nod of approval there from the corner of the screen. Oh, yeah. Yeah, yeah. Oh, yeah. Oh, yeah. That's probably what I was saying under that face mask was, oh, yeah. Oh, yeah. But the idea is, if you can get these perfectly lined up, it works. If you can't get them perfectly lined up, it's not going to work. But we see once again that does work out. Yeah, it's pretty fun. Yeah, so that's all right. Okay, let's get back to work here, and let's see where we're at here. Okay, so let's go to this one now. All right. So now I show you that for this reason. This is actually very similar to a car going around a flat turn. It looks a little bit funky because the car drives around in a circle, whereas in the previous problem, if you look at it, the masses were going around in the circle because the road itself was spinning. But the physics is nearly identical when you look at the FBD. If we look at the FBD for this thing, right, there's a normal force up, there's friction towards the center of the turn, excuse me, and there's mg. And so the FBD ends up being identical. Now, wait a minute. We need to talk about frictional forces involved with tires. Somebody unmuted. Was there a question? Go for it. Was that a question or no? Okay. All right. All right. Sorry. So this one, I think this topic is particularly confusing. Oh, there is something there in the chat. Okay. Yes, Jacob, that would be, well, we got to be careful. You'd need to get a 50-pound mass that has exactly the same coefficient of friction as the penny as well. So now if they would both fit in the same box, it should work. An empty box versus a box with 10 bowling balls in it should work. In practice, actually, the next thing I'm going to say might relate to that a little bit. So, all right, so let's go down a little bit. So this is at the bottom of page whatever we're on. I don't know what page we're on. Let me see. 116. 116. All right. So when you're driving in a car or riding a bicycle or if you're walking on carpet, this always happens where either the road gets smashed a little bit, like the carpet. Whoops. Hold on. There we go. So, or if you're driving in a car, you could imagine your tire is not perfectly cylindrical because the bottom of it gets smushed a little bit. So when you're driving in a car this way, and I'll just kind of draw the rest of the car really quick. This is kind of a weird car, but whatever. The idea is the tire gets smushed a little bit. It takes energy to smush and unsmush the tire. Just like when you walk on carpet or roll a bowling ball across carpet, you could, I know you're doing that tonight. We're all going to be rolling bowling balls across our carpet tonight. I'm sure of it. But when you do that tonight, you might notice the carpet gets squished and unsquished, just like in this case, the tire itself would get squished and unsquished. There's a type of friction associated with that squishing and unsquishing. That's called rolling friction. Rolling friction is not given by friction equals mu times the normal force. That's sliding friction. Now, imagine if all the cars in every physics problem jacked up the air pressure in their tires so that squishing was negligible. That's what we are going to assume. Okay, so we're going to completely ignore rolling friction. Now, that rolling friction is a force that opposes your motion. So that's friction due to rolling. That is not what we're going to talk about. If we look at this picture up above with this car, the car is rolling into the page, and we're ignoring friction out of the page, right? We're ignoring the rolling friction towards us out of the page. However, there is sliding friction towards the center of the turn, and that is mu static, right? Or sorry, F static, not mu static. It's less than or equal to mu static times the normal force. So in all of these problems with cars driving around turns, yes, there is friction opposing the motion, but we're ignoring that. We're assuming that motion is negligible. If you push a car just on a flat level road and let go of it, it's going to roll a little bit. And so that means that rolling friction is to some degree negligible compared to this static friction that's keeping it in the turn. Any questions about that before we go on? The static friction is not the friction. Well, wait a minute. Isn't the tire moving? Should it be static or kinetic?
Kinetic?
Static. This is mind-blowing here. When an object rolls without slipping, the point of contact with the ground is not moving. So get this. You could be driving 200 miles an hour. Part of your car is not moving. That's the bottom of the tire. Now, wait a minute. That's got to be bullshit, right? Let me get my handy dandy. Now, this is a little bit weird. It seems bullshit, but it's not. This is actually a fact. So what I want you to do is look at this spot right here. Pretend my arm is the roadway, right? Now, whoops. Okay. Jeez, there's too many strings here. Okay, let me do this. There we go. Okay, so look at this spot right here. Okay, now right before it hits the ground, so this is supposed to be level ground. Right before it hits the ground, which way is it moving? Right, left, up, down, predominantly. Which way is it moving right now? Just the whole, just this.
Down.
Down. Right after it hits the bottom, which way is it moving?
Up.
Up. It's going down right before, up right after. How fast is it moving right at the bottom?
It's not.
0, right? So now where this gets crazy is at the top of the wheel, it's actually moving twice as fast. So when you drive 60 miles an hour, the cop could say, hey, the top of your tire was moving 120. I'm pulling you over. But then you just say, well, I took physics. That doesn't work on me. All right. I did actually use physics to get out of a traffic ticket once. And I used physics to fight an insurance company once. It's the only time it's come in handy in my life. That, and I guess paying my bills. But whatever. All right. So this is pretty crazy. But right before the wheel goes down, right after it goes up, the point of contact with the road is not moving at all. We'll revisit that in chapter 10. Moral of the story out of all this, it's okay to use static friction at the bottom of a tire. That's what this was. Yeah, it's really crazy. And I have to say it because if I don't, somebody says, that's bullshit, dude. And I'm like, well, it's not bullshit. It's just reality. It's just very strange. Okay. So not trying to waste time. I just want to point out it's okay to use F equals mu static times the normal at the bottom. Yeah. Okay. All right. Whew. So now we're up to 117. We looked at this very briefly last time. It turns out this problem is in every physics class because it forces you to think about coordinate systems a lot. Are we all going to be building banked curves? No, we're not all civil engineers here. However, it forces you to think a lot about what direction should friction point. It makes you think about what condition is valid for friction. Is it less than mu static times the normal force, equal to? Forces you to think about friction deeply. And again, coordinate systems out the wazoo. So last time, I think we looked at this one, and just to remind me, just kind of run me through the FBD really quick. What direction is the normal force in this problem? Is it up, down, right, left, parallel to the plane, perpendicular to the plane? Normal force.
Perpendicular to the plane.
Yep, so there's the normal force. All right, now in this one, it says patch of ice, negligible friction. We don't have to worry about that. What's the other force?
Mg going down.
Mg straight down. And what direction is this one accelerating?
To the left.
Left. Okay, we did this last time. Now, in the next problem, let's read this. 6.61. It's similar, but now we do have friction. It says, if we assume the car is on the verge of slipping to the outside of the curve, what direction does that mean? Friction points.
Parallel to the curve? I mean, to the
Okay, parallel to the plane, I agree. Which is perpendicular to the normal force. Which way? Up the plane or down the plane?
down.
Down, right? So if you're going, in this case, would you be going fast or slow, do you think?
Fast.
Fast. When you're going too fast, you need friction to hold you to the inside. If you're going too slowly, friction would point the other way. Now it says it's on the verge of slipping. Ding, 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 ding. What can I use for friction?
Static.
Less than.
Equals. If it's on the verge of slipping, equals. Okay. And so notice it even says here, determine the minimum coefficient of friction. So that's another key word, minimum. You're like, when I see that word minimum, usually that means it's on the verge of slipping. All right. All right, so got it. In this case, which coordinate system is the wisest to choose? So look, we're trying to get the minimum coefficient of friction. We could choose any coordinate system we want. Do we want one that's straight up and down, or do we want one that's parallel to the plane and perpendicular to the plane? Those are the two obvious ones.
Parallel, so we can be in agreement with friction.
Sorry, say again. I
The
cut out.
parallel one, so we can be in the same spot.
Yeah, I
Friction.
like this one because then friction will be in one of our equations and we don't have a cosine or a sine on it. And so hopefully it's easier to solve that way. Either one should work. Either one is okay. Let's go look at it. Whoops. So you could predict what the force equations in FBDs should look like. Will I get to there? There it is. So I show two styles here. All right. I'm going to pause for a second and let you see if you have any questions. And I think after this problem, we'll take our break, but let's get through this one, okay? I'm going to write up some of those equations on my whiteboard, and then we'll play around with it, and I'll show you how we get the answers. Hold on. Any questions about that while it's all up there? Either one works, but generally speaking, right? If I'm trying to solve for something that's got an F in it, I would use style 1, or the normal force, I would use style 1. Whereas if I was trying to solve for the speed or radius or something, that appears in AC. So I would probably use style 2. Okay. And notice the main issue is AC has to be split up into components if you choose that style 1 coordinate. You should know both of these. We discussed this last time a little bit. So let me see here. We're doing F and that is the parallel. Okay. I'm just writing these equations and we're going to play with them in a minute. Perpendicular is N minus mg cos equals MAC sine. Okay. All right. Whoops. So this was from the force parallel and force perpendicular. Now, because we're on the verge of slipping, I know this is going to be mu static times the normal force. So a trick you can do here is try and get F all by itself and N all by itself and take a ratio. So in this case, this is going to be F is equal to minus mg sine theta. And if I flip this one around, the normal force is equal to wait, that's plus, isn't it? Yeah. So again, I just moved this one over here. It became positive. And here I moved this one over there. It became negative. All right. So here's the trick. If I want to determine mu static times the normal force, because we're on the verge of slipping for this particular problem, I could say mu static times the normal force. And what should I do here? I take this side and divide both of these. What drops out on this side? N. What drops out on that side, everybody?
Mass.
Mass. Every term has a mass. So it's okay to divide it out if every single term has it. All right. Now let's go take a look at the solution, and I want to show you something. Usually this is written a different way in almost every physics book. It's usually written more like this, where there's a tangent theta in there. What? How are you going to get tangent theta out of this junk? Ideas? Pick one term. Oh, go for it.
Well, so I don't know exactly how to do it, but I know, so tangent sine over cosine.
Aha, yes. So do you agree we need to divide this by cosine to get a tangent?
Yes.
If I do it to one term,
You have to do it to the other term.
and that gets rid of the cosine over here, and I have to do it here, and I have to do it here.
Okay, yeah.
You see it? So well, the trick is you could divide every single term by cosine. Those become tangent. Similarly, we could divide every single term by g. That's going to get rid of this, and I'll get an AC over g. So by doing this, you actually get tangents. And see, I get the g on the bottom. I divided every term by g cosine theta. Okay? Every term, I should write that in here. Say divide every term by g cosine theta, and you get this. But so notice v squared over r is from the AC. There's the g, the cosine dropped out, and then you get a tangent, and it all works out. So showing the screen again here, right? You divide by G cosine. Whoops, I think I forgot to write the G there. Divide by G there. So if you divide by G cosine, this term just goes to tangent. This term goes to V squared over RG tangent. Here I just get a 1. And now from experience, when I'm working with these circular motion problems, so many times I see this. You'll see this a lot where you'll get an equation where there's a plus in the numerator and a minus in the denominator or vice versa. So very often you'll see these types of problems in circular motions with angles result in these equations where one of the terms has got a plus and a minus and the tangent theta switches. So notice in the top, tangent theta is with 1. In the bottom, tangent theta is with this V squared over R term. Now, what units should the coefficient have? What units does a coefficient of friction? Well, let's remind ourselves.
Nothing.
Nothing. Remember, friction is fun. Friction is fun, and you change it to a mu. And so if we look at this, this is in newtons. This is in newtons. Mu has no units. This is a cool reason to write this that way as well. When we see this, no units, well, V squared over RG, well, this is meters squared per second squared. This is meter times meter per second squared. It works. Tangent theta, no units. No units times no units. So no, it actually works out. So these are the kinds of problems you could use to check your units. And now, as a side note, one of the things you could do on test day, you know, someday we might have a test, you could always check the units at an intermediate step. If you're like, does this equation make sense? About the only tool you've got right now in your quiver that you really understand is checking the units. Later on, we'll learn more tricks, but right now, that's a good check. You don't have to wait till the end of the problem to do that check. You could do it early in the problem. That's what I'm saying. I don't know. Let's see if there was anything else before we take our break. All right, so look at this. Whoops. So you get this, notice if you go for slow speeds, friction flips directions. Look what happens to the equation. You still have the tangent thetas in there, but it looks like the minus sign gets flipped. So, and I don't know if you could tell here, the minimum value of mu versus the angle of the curve takes on this unusual shape. Notice, what does this tell you right here? All right. So it looks like this must be some ideal angle because you don't need any friction right at about 25 degrees. So you could go ahead and do that one, and I ask you to do that. Basically, you'd set friction equal to 0 and then solve for theta. All right. Yeah, if you care, racetracks usually do not exceed 25 degrees. All right, that's fine. Whew. Whew. Let's take a quick break. So let's come back at 6 and hit it hard, finish strong, all right? All right, you guys were that was pretty long. That was a good job. 10-minute break. All right. Round 2N, where N is the number of classes we've had, not your breakout room number. All right. Holy cow, I'm getting a little foggy here. It's been a long day. Man, I haven't had a day off in weeks. I've been working a lot lately, so I know your pain. So when you guys are out there working your asses off, I'm probably right there with you, all right? It is crazy. Multiple 12, 14, 10-hour days in a row. I'm just sick of it. But, you know, someday we'll be there. I was posting video. That was probably the lab tech. So we made those videos over the weekend and the lab tech posts them for me. And so he was probably posting them. Yeah. But I routinely work at like 5 in the morning until 8 at night or 10 at night. So no, yeah, that wasn't me. I have limits. Yeah, nothing good happens past midnight. All right. I just make too many typos. All right, sorry, I'm eating a sucker here. I'll hit mute while I get the next problem ready. So a couple of these other problems, again, in all of these problems, there's the same issues. There's coordinate systems, which way does friction point, which frictional condition applies. So that's why there's so many of these on here. That's fine. Let's look at this one now, 6.64. All right, and I'm going to blow this up a little bit here, but I'll give you a second to read it. You're going to see this sometimes in physics problems where a car is going over a hill or on a ramp or something. And what physicists do is they say, well, look, at any point in this turn, we can model the curve as a circle. The curve itself is not a circle. It looks almost like a parabola or something. So imagine if you were at this point on the circle. This actually, this point on the parabola, it looks like a circle, but with a much different radius. And this is kind of something I was alluding to. Sorry if my picture's not very good here. But the idea is each point on a path could be viewed as circular motion, but the circular motion has different radius at different points. And so that's what I'm kind of going for here. But a classic case is just to consider the top or the bottom of a curve, because usually there's something interesting at the top and the bottom. So now we have a mass M. There's a frictionless hill. It's sliding. All right. And now in this case, you might be wondering, up till now, I've been ignoring the size of objects. What if the size of the object matters? Well, in this case, let's say that's the center of the object. That is actually where the gravitational force acts. And so the radius of circular motion is actually this distance. So sorry if this isn't perfect again. So the idea here is the block itself is not moving in circular motion with radius r. It's actually, well, if the height of this particular block is r over 4, this distance must be r over 8. Give me a second. So that distance is r over 8. And hopefully you agree if you add 1/8 to 8/8, you get 9/8. So we could see in this case, if we ignored the size of this particular block, we'd be off. 1/8 is 0.125. We'd be off by 12.5%. So the radius actually needs to be at the center of mass for circular motion. Now, why am I mentioning this? Just because if I don't, students ask, basically. So I'm just trying to clarify something. If you look at this view right here, imagine we have a string, a ball on a string, right? If I have, let me get this up in here into my hands just so it's not distracting. In this case, I just want to point out for this particular ball on a string, the ball is actually pretty decent size compared to the length of the string, right? The radius of the ball is right here. 1, 2, 3. It would be something like a 20% correction to ignore the size of this ball. However, if we go all the way out here to this, now for this ball on a string, the size of the ball is pretty negligible compared to this huge distance here. So in this case, we might actually ignore the size of the ball, whereas in this case, we might not. And I just wanted to point that out. That's what this first question is all about. Any questions on that? Basically, the idea is if an object is big compared to the radius, consider the circular motion about the center of mass of the object. We will discuss center of mass ad nauseum in chapter 9. So let's learn more about center of mass then. All right, let's get back into this. Okay. What's one force acting on the block? At the very top.
mg.
mg, which way?
Down.
Straight down, got it. What else?
The normal force going up.
Up. What is the force that keeps it moving to the right?
The wind?
There isn't one. We don't need a force to keep moving. An object in motion stays in motion. So I was trying to trick you. I got you. My bad. My bad. All right. Now, what if this was a car? You mentioned wind. What if we were doing the same problem with a car driving over a hill? If we had a car driving over a hill, what is the force that makes a car go forwards?
The friction?
Friction. However, air resistance is not negligible for a car. So we could actually do this same problem for a car if we assume that it's moving at constant speed. If it's moving with constant speed, which component of acceleration is 0?
The A10.
A10. So if it's moving with constant speed or right at the top or bottom of a circle, usually we assume A10 is 0. So oftentimes for this problem, the horizontal forces usually cancel for these types of problems in a physics class, not always in the real world, right? You could be gaining or losing speed at the top or bottom of a hill, but we're oftentimes going to ignore the left-right forces, and then it just becomes this simplified model where there's we can ignore friction, all right? Or friction is balanced, either way. All right, that said, which way is this block accelerating? Up, down, left, right. So ignore this now.
Down.
Down. AC. What's the force equation? Take a second, everybody. Take a second to write down what you think it is. Where's my water? My gosh, I forgot it. Whatever. What's the force equation now? Give it a shot. It's okay to be wrong.
Sorry, velocity equals MAC?
Wait, velocity equals MAC?
Uh-huh.
All right, that is not it. So check the units. This is meters per second squared, right? This is kilograms. What's the units of V? Meters per second.
Yeah.
So that was a good idea, but it doesn't match up. Remember, velocity is not a force. Also, you can see in this picture, velocity is going this way, AC is going that way. So that's not a good idea. Good thought, though. I appreciate you giving it a shot. Anybody else want to give it a crack?
Wouldn't it be? Oh, go ahead.
No, Dana, go for it.
Okay, would it be N minus mg equals, I guess it would be minus MAC.
Beautiful, dude. Beautiful. So he said up is positive, and then he was about to change it to negative, I could tell. But he said N minus mg is equal to mass times AC is opposite the coordinate. He caught that. Nice job, dude. This is one almost everybody misses. All right. So now, Dana, what were you going to say next?
I was just gonna flip it around, make everything.
Make
Positive.
down the positive, right?
Yes.
So generally speaking, this is what I often do. So if you flip the directions, this would become negative, this would become positive, and this would become positive. So a lot of times what I do when I'm drawing these FBDs, you'll see it. Give me a second here. Right? A lot of times what I do is the default in my brain is to say, okay, this is the positive direction. So I know that these two have to have the same sign. This one has to have opposite. Let me check the chat. Okay. Yeah, plus, minus. Yep, totally. It's always in that plus, minus. All right. So when I do it that way, I get n, negative n plus mg equals MAC. Same equation, but whatever. All right. So if I solve this for the normal force, what do you get? Mass times what?
G minus AC.
I think so. Let's write it down and see. G minus AC. That seems reasonable, I think. So let's see. The N goes over here. G stays positive. Yep. And let me check the chat here. Yeah. That's all right. Cat on the keyboard. It happens. Okay. All right. So in this case, let's think about this. What happens if you go faster and faster over the hill? So let's say the first block went over at 1 meter per second. The next one goes over at 1.5 meters per second. The next one goes over at 2 meters per second. What happens to the normal force for each successive block? If you go faster, what happens to the normal force? That's what I'm asking.
It decreases.
It decreases. What happens if you go too fast?
So AC is going to eventually go negative on the right side. So then it's going to get too small.
Okay. I think somebody else unmuted. What were you going to say?
I was gonna say it would catch air and would it be
You'll catch
projectile?
air. If you go too fast over a hill, you lose contract. So remember, Jacob, we cannot get a negative value of a normal force usually, right? This is a normal force magnitude. So we expect that if you go too fast, you become a projectile. So, if you're losing contact, well, how do we want to find the speed you could drive? I set n equal to 0, just like before, and rock it out, okay? So, and you could think about what happens if the radius gets bigger, right? If the radius gets bigger, should it be easier or harder to catch air?
More difficult.
Yeah. What is the radius of a perfectly level road?
0?
Infinity.
Oh,
And now think about it. If you're driving on a flat road, AC equals V squared over R. Well, a flat road has a radius effectively of infinity, like let's say the Earth's radius, which is 4,000 miles, right? So if you're driving on a flat level chunk of road, technically its radius is 4,000 miles because we're on the planet Earth. But V squared over R, if R basically goes to infinity, AC goes to 0, and then you're just driving at constant speed in a straight line. It makes sense. This is not outrageous. All right, so this even works for a flat level road. All right, so now I want to go back a little bit. In this case, we had a maximum speed. In the bucket of water, there was a minimum speed. What was the big change that gave rise to this Significant difference. When you swing the bucket of water versus this one, what was the difference in the FBD?
Did the coordinate system flip?
Nope.
Just the normal force, right?
The normal force flipped. So sometimes you've got to be careful. These problems look very similar, but when we're in a bucket of water and the normal force was pushing down, that meant there was a minimum speed before you lose contact. In this one, when you're going on the outside, there's a maximum speed before you lose contact. So the physics is the same. Anytime you have a problem where somebody loses contact, set normal force to 0. Okay, if you lose contact, set normal force to 0. Do an FBD, solve for something. Now, in general, the mass looks like it drops out all the time. However, in these particular situations, it only drops out if the normal force goes to 0. So if I could, I'm going to fast forward a little bit. Give me a second. I'm going to skip forwards a few problems. Whoops, I just passed it. So in a problem like this one, notice the answer explicitly states mg is in there. So if you have a car that's driving over hills, you could see this is a good problem to practice. So maybe you don't want to catch air. So this problem will say what happens to the weight on you. If you've ever driven from, say, if you've taken 166 past Maricopa over to Bakersfield, there's that section of the road where there's these rolling hills like this, and you can make your kids puke or whatever because you can go too fast and get air, or not. I don't know if that could be done. All right, moving on. Let's get back to physics here. Anyways, so all right, enough on that. Let's look at this one here. Conical pendulum. All right. So we're looking at 6.65. I forgot what page we're on. Page 118. 6.65. Conical pendulum. So hopefully you have that there in front of you. I'll let you read for a sec. Give me just a second. This is the idea for the conical pendulum. All right. So you get this thing going. There it is. I'm going to try and slow it down a little bit. Notice it's going around the marker. Okay. And so this is kind of a sneaky problem. Obviously, there's a tension force on the ball, and there's obviously mg. Let's ignore air resistance. What do you think should be true? Is the tension more than, less than, or equal to mg in this case? What's your gut tell you? Take a chance. It's okay to be wrong. You'll remember the correct answer more if you try. Sorry, I'm trying to focus. What do you think? Is the tension bigger than, less than, or equal to mg? What's your gut tell you?
Bigger than.
Okay, why is that? What are you thinking?
Well, so for one, it's not falling.
Okay.
And for two, it's being pulled in another direction, like around. So I feel like it's has to overcome gravity.
So what you're saying is there's an mg down. Hopefully this is on the screen. Give me a second. There's an mg down, and the tension has to hold that up. In addition, there's another component towards the center. Now, in these problems, usually this angle up here is theta. Whoops. So what's this angle right here?
Theta.
Theta. And now, in this case, we could see right away This component of tension had better be mg or the ball falls down. You add in a second component. You're absolutely right. You got that one. All right. So there's our FBD. Is there any acceleration? I'm trying to spin it at constant speed now. If I spin this thing at constant speed, is it accelerating?
No, A10 is 0, right?
A10 is 0. So constant speed tells us A10 is 0. So is there any acceleration at all?
Is there still AC?
There still is. Which way? Up, down, right, left, parallel to T, what?
Towards the center, so parallel.
Yeah, so in this particular instant, when the ball's on that side there, when the ball's over here, you got to tell me, like, how about you say up, down, towards me, or away from me?
Away.
Towards. This is the part that's unbalanced. AC is towards me. Remember, it would go in a straight line if I let go of it, right? And so this tension is pulling it towards the center, this component of tension. So far, so good? What do you think?
Yeah, that's what I meant. Yeah.
Does it matter which way it swings? So this way it's going, no, what if I reverse it? Does any of the physics change?
No.
No. Same this way as this, as that way. All right. So in this case, you could do an FBD, write the force equations. We're good to go. Let's look at this one. Whoops. Sorry, let me get it on screen again. Okay. And so, all right. So I'm going to let you guys do that one. I want to move on to this next one, orbiting nuts. It's very similar. All right. Notice these two FBDs look very similar, but let's do this one because I actually have this one. I have a video for this one. All right. So it's another fair ride. Maybe you've seen this one where they get in swings and swing up. Things are initially at rest, and initially the swings are hanging down. Gradually, the ding, 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 ding. What does this tell you right here? What does that line of text that I have highlighted tell you?
A10 equals 0.
A10 is 0. So that means approximately 0. Good. So gradually it's speeding up. So that means A10 is not 0, but it's so close to 0 we can ignore it. Okay. And then at this point, the ride is rotating at a constant rate. Okay. Okay. They form greater and greater angles from the vertical. What's your gut tell you here? If you have different people on this ride with different masses, who's going to swing out to the largest angle? A heavy person or a child? What do you think? So let's say I put a kid on here and their mother on the next one over. Who's going to swing out farther, do you think? The kid or the mother? Assuming the mother is bigger than the kid.
Are they both the same?
Very good, Grasshopper. All right, that was pretty good. So you kind of know, we've seen this today where there's these things. So what are the forces acting on it? Give me a force.
Tension.
Tension. What's another force?
mg.
Mg. What's the force that pulls it to the outside? What's the force this way?
There is no force.
There is no force. The string pulls it towards the center. Good. Good. I love what I'm hearing. And it accelerates towards the center, right? It's exactly the same problem as before. The only difference is what's the radius in this problem? Right? Because isn't AC equal to V squared over R? I need a radius. Tell me what the radius is.
Is it just R?
Nope.
Is it 2r plus whatever L, the coefficient of it, like L cosine theta?
Let's take a look here. So give me a second. Let me clear out this. Let's start with the previous problem to get a feeling for it. In this problem, I'm just going to draw it. Do you agree this is the radius? That pink line is the radius. What's the radius?
AC?
No, AC is a, so here is something tricky. The FBD looks like this, and the acceleration is over here. This is just a picture showing the geometry of the object. Everything here, L has units of meters. What's the length of each side of the triangle? It's got to be meters. Let me see what's in the chat. L sine is correct. So this is L sine theta. Does that make sense why I'm not saying it's AC? This is a distance triangle. And so we see one more reason circular motion kills people. I draw this one. I've actually drawn several different photos or several different pictures, right? Because there's a one for the radii and the lengths, and then there's a separate one for the FBD, where this was tension, mg, and AC. So you need multiple pictures in these problems almost every time. So get used to drawing pictures and do yourself a favor. Try not to draw them so tiny. All right. So now let's go back to this one. This is the radius. What is it?
2r plus L sine theta?
Nope.
Would it be 2r plus 2l sine theta?
No, sorry,
Nope.
it's r. It's
Yes.
r plus
This
one.
is half of 2, right? 2r is the diameter. This is r. So it's r plus L sine. Got it? And we see one of the frustrations is you have to be good with geometry and looking carefully at the pictures. Now, do you guys, I don't know if you recognize that at all, but we could work this problem out and we're going to get a result. Let's maybe look at it really quick. Hold on, let me go to here. 6.66. All right, so here's the upper problem, and here's the lower problem. You guys recognize that equation? Does that look vaguely familiar to you?
It looks like the projectile.
It's problem 1.42 in the workbook. So you may think all these things that I pull out of my ass in these workbook problems are total bullshit, which I guess they are, but they usually relate to some other bullshit later in the class. Every little nugget, every nugget is precious. So it's very hard to do physics. There's so many things out there. You have to be good at communicating, coding, concepts, calculations. Yeah, anyway, so it just takes more work than other classes. And all right, anyways, look at this crazy result. I was trying to figure this out, but notice what doesn't matter in this equation. Mass. The mass doesn't matter. And that was what we were kind of looking for. So let me see if I can find it now. Okay, so same thing here. Oh, whoops, sorry. So again, it's kind of hard to see here, but there's a string wrapped around this axle that's coming up here and over this, and then there's going to be a hanging mass that falls down. And that's what's going to cause this to gradually accelerate. Now I'm playing this at quarter speed. Let's just get into it and watch it and see that there's no lie here. Here we go. Quarter speed. So notice one of those nuts is really, really tiny, and one of those nuts is big. But look at the angles. They're both tied to the outer, they're at the same radius. What do you notice about the angles every time it goes around? As it speeds up, the angles increase, but they both remain the same as each other. So there's that hanging mass falling down. And as he's, look at it, man, now that would be a scary fair ride. Can you imagine being on that? And then when I stop it, things get all messed up. All right. So that's that problem. And here's another version of it. These are two equal nuts held at different radius. So this is kind of cool. The one at the larger radius, do you think it's going to have a smaller or larger angle? What's your gut tell you? So again, these are two equal nuts, equal mass nuts, and one's at a larger angle than the other one. As we run it, I hope you could see that the one closer to the center doesn't need as much force to go towards the center. Why? It's not going as fast. It needs less tension to cause AC. Now, one of the things here, I probably could have done a little bit more gradual acceleration here. I probably should have used a slightly smaller mass. I don't know if you could tell, but actually the string is not only pulling straight towards the center, it's actually pulling it slightly forwards, and that's to be expected. So to be clear here, in this case, this is not a pure, I guess this is a very challenging thing to try and describe. Instead of just being straight to the right, it's actually a little bit behind in the circle. And so there's a slightly forwards component there, which makes this tricky. And if you don't have that forwards component, you're not speeding up. So the angle is not, strictly speaking, straight out to the side. But as long as we speed it up very gradually, the amount of tension you need in the forward direction is negligible. Okay? Whew. Questions on that? It's a good one. I'm going to go ahead, skip to another problem. Okay, this leads us to this thing, and I'm going to mention this here. Give me a second. I sent this to you earlier in an email. Whoops, let me get this one. Okay, and so this video does a really good job of explaining what I'm talking about on page 120. So now I've broken this video down. It's like an old 1960s movie with two old white dudes, just, you know, whatever, but it's still really good. Okay. And so these old white dudes did some ridiculous stuff. And they like built a building that they could have. They made one of their grad students run around in a circle, pushing the entire room around and stuff. It's silly. So, yeah. And I just want to point out these two things right here. I'm going to talk about it right now. If you want to see what these two bozos did, it's really good, even though it's from 1960. All right. Whatever. All right. So go ahead. Was there a question? Go for it. All right. All right. Sorry about that. Okay. So now let's look at this one. I want to talk about fictitious forces because this one usually drives students crazy at first. Okay. Imagine we have a ball hanging here. There's no friction. I'm going to get this mass here. So what's going to happen when I let go of this system? It's going to accelerate, right? Which way is the ball going to move?
To the left?
I could say no. I could also say yes. I need more information from you. What do you mean by to the left? To the left relative to what?
So do we need to define a coordinate system?
Okay, I'll do that. X, Y, done. Now what?
So left relative to the block.
It moves to the left relative to the block. Where does it move relative to the Earth?
It doesn't move.
Initially, it doesn't move much at all. However, eventually, it's tied to this car that's moving to the right. Take a guess which way it moves eventually.
To the right.
To the right. Here is the issue with this one. And so this is trying to elucidate this one. This is a large mass. It doesn't want to move at all. So a half second later, this is going to scoot over a little bit, right? Notice the string becomes angled slightly. Now you may say, doesn't that pull it up slightly? You're right. It does actually move a tiny bit up. But I would like to point out that a string like this versus a string that's angled just so slightly like that, it moves up a negligible amount. So again, to be clear, when the string becomes angled, it doesn't move up that much. Technically, it does move up a tiny, tiny bit, like maybe a millimeter. Okay, but the string is now angled. As soon as the string is angled, even though it's small, there's a component of tension in the x direction. Which way does the ball actually move? To the right, relative to the earth. And so this is very sneaky. And this is what they do really well in that video. That's very hard. They do slow-mos. They show you different things. They explain all of this very well. Now, in this case, I just want to point out that we see the ball move backwards relative to the human being. So the human being that's sitting here perceives that the ball moves to the left, but the ball actually moves to the right relative to the earth. This confusion is caused because we have an accelerated reference frame. Okay, and that's what that video is all about. You could read all this. Now, here's something crazy. From the little dude's perspective, and I'll get to the chat in just a second, there's a tension here, right? And then there's a force down here. It looks like there has to be a force to the left. There isn't, but if that student or whomever that little dude is said, let's pretend that there's a force to the left with magnitude MA. I'm going to pretend that's true. And then the little dude could say, if I do that, effectively the acceleration is 0. They would actually correctly compute everything. So this is called a fictitious force. There is no force to the left on the ball. Yeah, so Jacob, I asked you a loaded question deliberately to inspire this discussion. Okay, so it was a trick question to make us think. No matter what you did, I would have said you were wrong, right? Or no matter what you said, I could have said you were right. It just depends on the relative. And so we're just kind of clarifying that in this type of problem, when you have an object that's accelerating, it's very confusing if we just say movement. We want to talk about relative to what. All right. Now, in this case, this trick we can actually use to take a problem that's dynamic, that's accelerating, and turn it into static equilibrium mathematically. Now, think about this. If we do this problem, I hope you agree there's going to be some angle here. And we get this equation that looks like T sine theta equals MA, right? Well, mathematically, there's nothing wrong with saying T sine theta minus MA equals 0. And I just want to point out, this is effectively like saying, hey, there is a force that points opposite the acceleration. That's what I was doing right there, right? And so mathematically, this is legal. However, that isn't a force. Acceleration is never a force. Just because the math works out doesn't mean it's reality. Okay? Just like N equals mg does not mean N and mg are action-reaction pairs. This is a true mathematical statement that is sometimes convenient in chapter 12. Enough said on that. The same thing applies for in a car, right? You feel like you're pushed to the outside. You are not pushed to the outside. If you're sitting in this car going in a circle, the car is pushing you towards the center, right? There's clearly a normal force towards the center, or a frictional force or something. Let's assume there's a frictionless seat. Okay, friction's negative. There's a normal force from the wall of the car here. There's a normal force from the seat here. Let's say normal force seat. Let's say normal force from the door, right? There's mg down. And what I'm saying is, we know this thing is actually accelerating towards the center. But that doesn't mean you can't pretend it's a force towards the outside and get it right mathematically. So we perceive this force. You feel like you're pushed to the outside all the time. You are not pushed to the outside at all. You are pushed towards the center of the circle, or you would not move in circular motion. I can't say it anymore. It's crazy. You feel this in your body, and that's why it's so hard to believe it. You feel pushed to the outside. You are not. You push on the door to the outside. By Newton's third law, the door pushes you to the inside. Whenever you're pushing on the door to the outside, you perceive that you're being pushed out there, but you're not. You're moving in circles. All right. Crazy, right? All right. That's pretty insane. Where was I? I don't know where we were. Let me pause for a second. It's very uncomfortable feeling usually. What do you think? Any questions on that? Okay, foreshadowing a little bit. What do we have coming up? We have, actually, this is finally a week where you get to catch up. Work hard on your Chapter 6 homework. Come in with questions on Wednesday. Then you can ask those questions and we have some time to answer them, right? And here's the trick. If you can go through the solution and figure out the exact line in the solution where you have trouble, I can help you with lots of questions really quickly. And then you'll have lots of help for the quiz, which is in the second half, right? Or wait, I guess the quiz, I don't know. Maybe, I don't know. I'll have to think that through. The quiz is usually at the beginning, isn't it? But maybe what I'll do is I'll actually do this quiz at the end next time or something. I haven't thought that through. But yeah, I was hoping you could ask me questions on Wednesday and then we take the quiz Wednesday. So, yeah. All right. Any other questions before we quit today? I don't know if we got through everything I wanted to. Yeah, so I'll see if I could do that. I have to think carefully because I have LAP students and that complicates scheduling everything. So I got to think about that and find out if that'll work because they probably already made their plans. I need to think that through. Yeah. So I don't know if I'll be able to do it. All right. Anyways, other questions? Yeah, I do have office hours earlier in the day, right? And you're welcome to come to my other lecture if you want to for that day, if you want. I don't care. The other lecture is same Zoom room at whatever time it is, noon to 2:15. But I'll send an email after this class once